Hello, I'm sorry for the delay. Okay, so I'm not sure if this question is related to this part, to practical machine learning, but either way, it's a general question. So yeah, you can participate in the competition with your personal account. Just make sure that you put your name there, your full first name and last name included. So the links for participating in the competition are provided by the lab assistants. I will not put them on the site. So since we started with this topic, I'm going to show you. So I hope that everyone can hear me. Just let me know. So I'm not sure if this question is related to this session or to the previous one. But anyway, you have the competition here that is for the supervised. So we already have some participants, I see. So yeah, what you have to do in this competition is to predict the geolocation of tweets, of German tweets. So you can participate by asking your lab supervisor for the link. I actually asked them to share among all the students. You also have a link to the competition on this web page. If you want to access it from here, you can take a look at the competition, but you will not be able to participate from this link. You will need the link from your lab assistant in order to participate. So this is just a link to the challenge on Kaggle, not the link for participation. Okay, so yeah, so as I promised, your competition is launched. You can in order to participate, first you need to access the link, and you also need to understand and accept the rules here. So you'll see this page under rules, so you have to go and check this in order to participate. So here you have the rules, so you can do 2 entries per day, and in the end you can choose 2 submissions. The deadline is 3rd of January next year, so I extended the deadline because I also launched the competition a bit later. I also increased here the number of competitors for Mark 10, for grade 9 and so on. This is because initially I thought there are 120 students that are participating, but I learned that actually the total number is around 160 students. So I had to update these accordingly. So we have here some sort of Gaussian distribution for the grades. And please also be careful with the project documentation, which is the end here is detailed. If you require additional details, you can ask your lab assistants. So these are some general indications. So you need to provide your code, and also you need to prepare a PDF document that describes your approach and shows some preliminary results on the validation set. So we have a training set, a validation set, and also a private test set that is used to compute the leaderboard. So for the private test set, you will not have the actual labels. Okay, so yeah, these are the things that I wanted to mention about the competition before starting the lecture. Yes, Mihai summarized that accordingly, but Mihai, if you're from the practical machine learning, so if you're a first year master student, then you can ask your lab assistants for this link. For those that are on the deep learning course, then the competitions are not yet launched for them. I will prepare them in the next couple of days. Okay, so yeah, just drop in if you have any questions about the competition. Just let us know here. Now it's the same link for everyone, so the main idea is that you can get in, but please do not share the link with anyone that is outside. So you can share the link among yourselves, but do not share it with students that are not subscribed to this lecture. So I want to have a clean leaderboard without people from the outside. Okay, so this is why I didn't make the link public, so it's only shared privately. Yeah, so today we're going to discuss about neural networks, and so everybody can also try to test these models. I prepared the task in such a way so that there isn't a clear advantage of in using deep neural networks. So I assume that if you do not know anything about recurrent neural networks, I think you can obtain a good result even without using these architectures. But if you like to use more complex models that are not presented in our slides, then you're free to do so. So that is not an issue for us. So in the end, you can use any of the presented models or any other model that is not presented. So as long as it is based in machine learning and not some, I don't know, some heuristic that you try to, I don't know, to estimate the geographical location based on some explicitly programmed algorithm. That is not really what we want. We want to employ machine learning. So that's the only restriction. Yeah, so how do you post a score? You do not post a score. You just have you have some test data. So if you go to data, you have here these data. So you have some test samples, and you also have a sample submission. So for the test samples, you need to include the IDs of the test samples and also your predictions. So you can go to, I don't know, to my submission, or maybe here to submit predictions. And then here you can upload predictions. So you have to upload your submissions here, and you will get a score on the leaderboard. So this is computed automatically through the platform. It's not a score that you add by yourself. Okay, so this is also related to the question by Rafael. Okay, so I don't want to spend too much time talking about this competition. I will jump into the slides, and if you still have time at the end, we can also take questions on the Kaggle challenge. Okay, so today we're going to discuss more about loss functions and the optimization, and actually in optimization about the gradient descent algorithm. So we start with the slides from the previous lecture and with the loss functions that were introduced for the SVM and for logistic regression. So recall that last time we discussed about the challenges in visual recognition, such as intraclass variation and interclass similarity, which really pose problems for linear classifiers, and we need to make sure that the classifier is able to discriminate as best as possible these objects. So yeah, in the standard formulation, we use a linear classifier on top of some input image that is represented to some through some handcrafted vector of features. So here we have the vector x. We have these 1 versus all linear classifiers, each with its own vector of weights and the corresponding bias that produces some classification score. And in order to decide the class for this object, we take the score with the class with the maximum score. So this is done using argmax of the probability or the score that is predicted by the model. So we looked, if you remember, we looked at the multi-class SVM loss or the hinge loss, which is not optimizing until the very end. So recall that the loss for the SVM is the sum of the maximum between 0 and the score of the of some class minus the score of the corresponding class plus 1. So plus 1 is for the margin of the SVM. So if we compute, for example, the loss for this example, which is a cat, so we know that the true category is cat. So here the score for this category is x, y, I. So this is 3.2. And we have the loss with the loss is computed for the other classes besides the correct class. So if any of these scores is higher than this score, then we have a loss that is higher than 0. So in this case, we have a single score that generates a loss that is higher than 0. This other one is okay. For this example, the maximum score is for the correct class car. So here the loss is 0, even if the model predicts positive scores for the other two classes. Okay, and I'm going to skip this example. So the total loss is computed as the average of all these individual losses for the training samples. So we discussed last week that this loss is not optimizing the model through the end, and in order to make sure that we have a loss even for this image with the car here, we can use the softmax classifier, also known as multinomial logistic regression. So here we interpret the scores as unnormalized log probabilities of the classes. So from these unnormalized log probabilities, we want to transform them into probabilities, which can then be optimized by making sure that the probability for the correct class is 1. Okay, so yeah, in order to obtain the probabilities from these scores, we normalize them by dividing with the sum of all the scores, and we obtain the probabilities from the log probabilities by using the exponential function. Okay, so this is known as the softmax function. So it can be implemented in deep learning libraries as a layer. So in many cases it is a softmax layer. So what the softmax layer does is it transforms the scores into these probabilities, and the corresponding loss function will be minus log of this probability. Okay, so here we have the unnormalized log probabilities. We exponentiate them, we normalize them, and then we obtain probabilities. And then we have the loss corresponding to this class is minus log of this softmax loss. And if this is closer to 0, it will have a positive value, and it can also go up to infinity. If it's closer to 1, the loss will be lower. Okay, so yeah, we answered this question last time. So minimum and maximum values for this loss are 0 to infinity. The advantage is that for these examples, for example, using the hinge loss, the loss is always equal to 0, but for the softmax loss we get different values. So this one is the closest one to the value 0 for the loss, and this one is actually higher, so the model will actually try to learn and really discriminate between these data points. Yeah, and we also have the particular case for the binary classification. We have the binary cross entropy loss, which I explained last time. So these are also relevant because are commonly used in learning neural networks. So binary cross entropy and softmax layers are components in neural networks. And in order to optimize these neural networks, we use this loss function that we want to minimize, and in order to minimize it, we apply this algorithm that is called gradient descent. So the loss is a function in a multidimensional space that looks like these hills and mountains, and the goal of the algorithm, so we have a random starting point, and from that point we are trying to follow the negative direction of the gradient until we reach some place where the value of the function is lower, and hopefully in this location we have a good model that is able to predict I don't know, class labels or whatever with minimum error. Okay, so in the main algorithm that we use to optimize these loss functions is using gradient descent. So in one dimension we use the gradient is just a derivative of a function. So in one dimension it means that the function has only one parameter x, and we can compute the gradient here in two ways, either applying the numerical approach, which is based on approximating the derivative with this limit. So we have some constant h that is positive and approaching 0, and we just compute the function for x and the function for x plus h, and then we subtract, we look at the difference, and depending on this difference we can say something about the derivative, if it's positive or negative. So we're mainly interested in the direction of the gradient here. So, but actually this function approximates the derivative as h is closer and closer to 0. Okay, so this happens in one dimension. In multiple dimensions, so as I said before, we're optimizing a loss function, and at least the loss function has the parameters w of this linear classifier. Actually we are optimizing a function in multiple dimensions, so the gradient is actually a vector of partial derivatives in this case. And when we optimize it, we can actually optimize it on each independent component. So we have let's say the current vector of weights on the left side, and the corresponding loss value. So this is our function f. The function f is the loss function. So we have this value here, and we add this small constant to the first component of the weight vector. We compute the new loss function. So this is f in x plus h, and then we just subtract these from this and divide by h and obtain an estimation of the gradient. So we subtract f plus h minus f of x. Sorry, this is f of x plus h, and this is f of x. We divide it by h and we obtain this value of the gradient. So now we have an estimation of the gradient for this component. And we do this for every component in our vector of weights, and we obtain the corresponding gradients. So yeah, this is the numerical approach, which is costly because it needs to compute the function f twice, and of course a better solution would be to use the analytical approach. So the numerical approach is also slow and also provides an approximate value, not an exact value of the gradient. So for the analytical approach, we need to do some calculus in order to determine the gradient's formula. And actually, in practice, when you train these models, the gradients are automatically computed for you by these automatic derivation frameworks like TensorFlow and so on. So you do not need to take care of this in practice, but I'm explaining these details for you to actually understand how the algorithm works. Okay, so suppose that we have this function f with a single parameter x, and it returns an output y. So in order to estimate the gradient with the numerical method, we can estimate the gradient like this with a small h. And using the analytical method, it means that we have to have the function f prime. We have to know the definition in order to compute the value of f prime in the point x. Okay, so these are alternative ways to compute the gradient. Once we have computed the gradient, we can apply gradient descent. So yeah, so far we discussed about the numerical gradient and the analytical gradient, which is exact and fast, but it is also error prone. When we define custom functions, in some cases we also have to provide the derivative. So in order to make sure that we do not introduce any errors, we can also verify the gradient with the numerical values. So this is called gradient checking. Okay, so gradient descent is actually the taking the current w, so this is the current vector of weights, and taking a step in the negative direction of the gradient. So this is the gradient of the loss function, and the magnitude of the gradient is also adjusted with this learning rate, or also known as step size. So because in some cases the gradient can have a very high magnitude, then the model can actually take a step in the right direction. But if it's a very big step, it might go to a location that has actually worse. So you can imagine if you take in this direction, you take a step in a good direction, but here actually the function may continue like this with a bigger loss. And if you take a very big step in this direction, you might end up in a place that is not optimal. So we need to make sure that these steps are not so high. Okay, so in Python you can implement gradient descent as a function where you have the parameters w of your model, the input data x, a goal which can be used as a stopping criterion. So as you approach the local minima, the update will be smaller and smaller because the gradient will also be lower. So when you approach the local minima, you will probably, so this gives you an idea of how well you approximate the local minima. So if you want to approximate it with 10 decimals, you can set the goal to 10 to the power of, I don't know, -4. And the step size or the learning rate, so these are the parameters, the main parameters of the algorithm. So here we have some starting point W0. So we start with W0 and we update W with in the negative direction of the gradient. And we have this function that evaluates the gradient for the data x and the current w. So this gives us the value of the gradients. It can be analytical or numerical. And then we have the stopping criterion. If the update is smaller than our goal, then we stop the algorithm. Okay, so yeah, before going to the next slide, I want to show you this example with gradient descent with the function that we defined in our slides. So the function is of this form. The derivative is f prime. So these are polynomials. This is a polynomial of a smaller degree. All right, so because this is the derivative, so recall that when you derivate here, this results into 4 times x to the power of 3. So when you multiply 4 with 0.5, you get 2 times x to the power of 3, and so on. Okay, so here we have an implementation of the gradient descent algorithm as presented in the slides. Here we have the option to compute the gradient using the analytical or the numerical form, and yeah, here we have the call of this algorithm from some initial location. So here the starting point is -2.8, which on the x-axis is somewhere here. So when you start here, you when you apply gradient descent, you update x in this direction and you reach this local minima here. So I also want to look at this graphical interpretation. So let's also try to see. So let me run this, and I think, yeah, I need to run it again in order to show the figure. So this time we started from this location 2.8, so it goes to this. So this function, this is the function f that we want to optimize. So this will be our loss function, and it has two local minimas. So we can either go to this one from this region, or to this local minima from this other region. And the green line is the derivative of this function. So why is the derivative important here? So if you look for this function, so what we want to do is to minimize the function. So if we are here, we want to go to a place where the function is lower. So in this case, we want to go in this direction. So if you look on the x axis, going in this direction means that you need to increase x. And actually here the function is decreasing. So when the function is decreasing, the gradient or the derivative is negative. So the function is decreasing until this local minima here. So the function is slowly decreasing, which means that the derivative is negative. And when the derivative is equal to 0, we have some inflection point, which can be a local minima. Then the derivative is positive, which means that from this point on, the function is increasing until here. So as long as the derivative is positive, means that our function is increasing. So in this case, the direction of the gradient, the negative direction of the gradient will point towards this direction. So if we are on some point here, we should take a step in this direction. Okay, so now here we have another inflection point. This time this is the local maxima. So from this point on, the function decreases until this point. So this is because on this region the gradient is negative, so it's below the horizontal axis, and from this point on the gradient is positive, which means that our function is increasing. Okay, so the derivative explains the behavior of our function, and we are using this gradient in order to take steps into a direction with a lower value for our loss function. Okay, so this is the main idea behind the gradient descent. Okay, so now, yeah, I explained how it works in one dimension. So if you consider this loss function in a two dimensions, so here in one dimension we have the one weight, let's say W, and the value of the loss is in on this axis. So the value of the function has value on takes values on the vertical axis. So here, if we want to represent this loss function in a three-dimensional space, so we have two parameters for the loss functions, loss function W1 and W2, and the value of the loss is represented here with this heat map. So lower values are in dark blue and higher values are with red. Okay, so here we have to compute the gradient for each independent direction. So this is what I explained earlier. So we take the gradient for W1, so it should be in the negative gradient should be in this direction. For W2, the negative gradient will be in this direction, and then when we update our model, it will take a step in this direction. Which is approaching the local minima. So computing the gradients independently on this axis is okay. The model will reach a lower point. Okay, so actually in practice we are using a version of gradient descent which is called stochastic gradient descent. So instead of using the whole training data at once, we are using only a small portion of the training set, and this has it is motivated because of the deep neural networks that we're trying to optimize actually need to compute a lot of gradients. So the gradients are matrices with partial derivatives. So if you want to compute this for the entire training set, is not feasible. So in order to be able to train the model, you just select a subsample of the data set. But this is also beneficial because it introduces some variation in the optimization process, which can actually help the algorithm to escape local minima and to converge to a better solution. Okay, so yes, stochastic gradient descent means that we are selecting a random subsample of our data X, and we evaluate the gradient on this random subsample, and then we update the W according to this. So mini batch sizes can vary between I don't know, one sample to I don't know, 256 samples. It really depends when you train neural networks on the size of your video RAM. So you usually train them using a GPU, and you can try to add as many examples that you can fit in your GPU. Okay, so and also because you introduce these random sampling in the training process, so for these subset of samples, you may take a direction in the negative, a step in the negative direction of the gradient for these samples. So remember that the function depends on W and also on X. So when you just keep only a small part of X, then the loss function will not be identical to the function for the entire dataset X. So you're optimizing on an approximation on the loss function, and when you do this optimization, actually you might take a step that is bad for the global loss function. So when you optimize the model, actually the gradient descent will not look as smooth, but actually it will have these patterns. So the loss might increase and then might decrease, but the general trend is that you can optimize the model like this, but locally in some small steps you can actually increase the value of the loss. And this also this generic trend is also regulated by the learning rate. So if you use a very high learning rate, the model can actually diverge to a poor solution. If you use a low learning rate, then the model will converge, but very slowly. It might take a lot of time, and you actually need to find the right step size in order to train your model. And it is also observed that it is better to start with higher learning rates. So here you get better optimization at the beginning with higher learning rates, and as you continue the training, you can decrease your learning rate in order to converge to the optimal solution faster. Okay, so much about the optimization process. Now thinking more about neural networks. So the main motivation with neural networks is to replace simple linear classifiers with more complex classifiers that can learn nonlinear decision boundaries. So this is a paradigm shift from standard machine learning approaches, where you, instead of designing some features from your input data, you try to learn them with your model. So in neural network, you just define some neural architecture, and then you try to optimize the parameters of your network such that it can take an input image and produce the output directly without having to handcraft anything else in the model. So yeah, now we're going to discuss more about doing gradient descent on this entire network architecture. So how is this done? So first we model the neural architecture, or we think of it as a computational graph. So for example, just starting with a linear model, so this computational graph can be framed as follows. So in a linear model, we have the decision function f is equal to the weights w times x. Yeah, and here we ignored the bias term, and we also have some regularization term, for example, on the norm of the weights. So this can be modeled as a graph. So we have the weights w, the input x, so these are multiplied. So these nodes go as input to this multiplication node. Then we obtain the scores. Then we apply the hinge loss, which is takes the maximum of 0 and these scores that are given here, and these are summed. This hinge loss is summed up with the regularization term, and we obtain the loss for the SVM. So the same idea of transforming the network into a graph is also applied into deeper neural networks. So here we have some input image, some weights that are used to multiply the input with I don't know, the learned weights, and we obtain some intermediate representations until the very end, where we have the prediction for the classes. Okay, and now how do we use the gradient descent to optimize this graph model? So here we start with a simple example with a function that has three parameters, x, y, and z, and the function is defined as x plus y times z. So suppose that we have some random initialization of these parameters x, y, and z. So this would be like the random initialization of the network of the weights, and also taking some fixed input examples for the network. So the function is defined as a graph like this. So we have the sum of x plus y, and the result is multiplied with z. So the value of this function is minus 12. And what we want to do here is to modify the parameters of the function x, y, and z in order to obtain a lower value for our function. So in order to obtain this, we look at the gradients of our components. So first we have the gradient of f with respect to z. So the gradient of f with respect to z is equal to q, where q is the sum of x plus y. So we use this notation here to simplify our gradients. Now we have also the gradient of f with respect to q, which is z. Okay, and here we also have the local gradient. So we have the function q, and we have the gradient with respect to x is 1. So this 1 times x plus a constant, so the constant goes away, and we have the multiplier for x, and the same we have the same gradient with respect to y. Okay, so what we want to obtain is to compute the gradients with our parameters x, y, and z in order to be able to update our function. So first we start with the gradient of the function with itself. So this gradient is 1. So now we want to compute the gradient with respect to z, which is the easiest one to compute. So we know that the gradient is equal to q. So since q is equal to 3, then the gradient is 3. Now we compute the gradient with respect to q. So the gradient with respect to q is z. So z is minus 4, so the gradient here is minus 4. And now how do we compute the gradient with respect to y? So the main idea that we introduce here is used to train neural networks and to pass the gradient from the loss function throughout the network through all the layers in the neural network. And this update rule is called the chain rule. So the chain rule is based on computing or on estimating the gradient of our function with respect to this input y as the product of the gradient of the function with respect to the output q of this node times the gradient of the local function q with respect to the input y. So this is applying the chain rule. So we have here the gradient of the function with respect to q, which is minus 4. So we know this value. We also have here the gradient, the local gradient, which can be computed by taking the form of q. So we know that the local gradient is 1. So this means that the gradient of f with respect to y is equal to minus 4, because here we have minus 4 times 1. And the same applies to the gradient with respect to x. So the gradient with respect to s is minus 4 times the local gradient. So this is also minus 4. So we also apply the chain rule here. And in general, for a node in a neural network, we have sorry, I just realized I have a mistake here. So suppose that we have these activations from a preceding node in our graph. We have a local node with that computes some function and provides some output z, and now we have the local gradient for this function f, and when we train the model, we first do a forward pass through this model in order to compute the value z from some specific values of x and y. And then when we update the gradient, we apply the chain rule and we obtain the gradient of the loss with respect to the current node z. And then we compute z with respect to these values here. So actually here this is also another mistake, so this should be the function should be z here. Or I think, yeah, no, we can keep the notation f, so z is equal to f of x and y. Yeah, so that's okay. Okay, so yeah, here is another example where you can, so yeah, I forgot to mention in this previous slide. So now if you try to update these weights in the negative direction of these gradients and recompute the function f, you will see that you will get a lower value for f. Okay, so another example here is with this sigmoid function so this is a neuron with two inputs, x0 and x1. So it has the weights w0 and w1. This is the bias, and here we also have the sigmoid gate, which is 1 divided by 1 plus the exponential of minus this input of this summation in the neuron. So this can be modeled as a graph like this. We have the weights and the input x here. We have some specific values, and here we see how we can so we multiply these, we sum them with the bias term, we apply here the sigmoid function, and we obtain this output, which is 0.73. We use these gradients of the local function. So here we have the exponential function, so the gradient of the exponential function is e to the power of x. Here we have the gradient for multiplication with the constant. So all these are used from calculus. So we also have here the gradient for 1 divided by x, because we have this function here in the sigmoid, and so on. So now we can apply the chain rule. So we have this gradient of the function with respect to the output. We have the local gradient, which is 1 times minus 1 divided by x squared. So here x is the input, so we can compute the gradient here. We multiply it with 1 and we obtain the value minus 0.53. And we do the same here. So here we have the addition with constant. So we have this local gradient which is equal to 1. So we have minus 0.53 times 1 is equal to minus 0.53. Now we apply the exponential. So the exponential of e to the minus 1 multiplied with this is equal to 0.2 roughly. Then we have this multiplication with a. So here the gradient is equal to a. In this case a is minus 1, so we multiply minus 0.2 with minus 1 and we obtain 0.2, and so on. Now for the addition, here we have actually the gradient for the addition is distributed. So when we have addition, the gradient is distributed. Once again, here we have addition, so we distribute the gradient. So this means that we multiply the gradient with 1 in both cases. And for the multiplication, the gradient is switched and multiplied with the corresponding opposite value. So here we multiply 0.2 with -1, so we get -0.20, and here we have 0.2 multiplied with 2, so we have roughly 0.39. So this is approximate values. So yeah, this is how we pass the gradients for this neuron with 2 inputs, so you can actually get an idea of how you can optimize this model as a graph by applying gradient descent. And yeah, one idea here is that we can also know use a single node in the graph to represent the sigmoid function. So this function is called a sigmoid gate. So the derivative of this function is equal to 1 minus sigma of x multiplied with sigma of x. So we can actually use a single node for this sigmoid gate and use this value of the gradient. So by applying, so now we know the output, so we know that sigma of x is equal to 0.33. So then we can compute directly this value as 0.33 times 1 minus 0.33, so we get roughly 0.2. So this is knowing the derivative for the sigmoid gate is useful here. Yeah, and what patterns we observed? We observed that the add, so when we add the gradient is distributed. When we have max, the gradient is rooted. So this is also important because we have activation functions that have max in their definition. So we will discuss more about the activations of neurons in next week. And for the multiplication gate, it acts as a switcher of the gradient, but taking the magnitude from the opposite input. Okay, another important aspect is what we do with the gradient when they branch out. So the gradients are simply added up. So the gradient of the loss function with respect to the output z is equal to the gradients that are collected for every branch where z goes to. So then if we want to train this graph model, we just need to define for every node what is the function, and what is the forward function that is computed, and also the gradient of the corresponding function. So actually this can be computed in two independent functions and called forward and backward. So when we do the forward, we use the function to compute the value z. So something like this. So this is an example for the multiplication of the input. We have the forward function that does the multiplication. But here it's also important to keep the input x and y for the backward pass. So there is some storage that is required here in order to compute the gradients. So now we have the gradients with respect to the input x is equal, according to the chain rule, as the local gradient of the function z with respect to x, which is the y. So we are using these values here, so this is why it's important to remember them for the backward pass, and this is multiplied with the local gradient. So the local gradient is dz, so this is given as input to the backward function. So the backward function takes as input what we get here, and it returns as output the gradients for the two branches. Okay, so if you implement these two functions for every node in your graph, then you can optimize your graph using gradient optimization. Yeah, so here we also enter this discussion. So you see that here you need to store these values in order to backpropagate the gradients. And usually we can apply these notations also on matrices and vectors. So actually here we can have x, y, and z are all vectors. So and the same rules apply. Only here that the gradient is not a single component, it's actually a Jacobian matrix that contains the derivative of each element in Z with respect to each element in X, and the same happens here, so the derivative of each element in Z with each element in Y. So now if we have, let's say, a layer with 496 units that outputs these 496 dimensional vectors, then here we have, for example, an activation function that is max of 0 and x. So this actually replaces all the negative values in our vector x with 0, and it gives us an output vector. So this is one component, for example, used in the AlexNet architecture that I showed earlier. And here we have the gradients. So this is a Jacobian matrix of the local gradient. So here we have the gradient of for every output and every input. And here the question is, what is the size of this matrix? So yeah, I would like you to give me an answer regarding this question. Yeah, so a question to Andrei Popescu. Yeah, I don't know. So how this guy entered. So he should use his username. Yeah, Lida got a good answer here. So here we have the we have the question. So for this case, the size is 496 by 496. But if we have more input vectors, indeed the Jacobian matrix is much higher. So we need to have the gradients of every actually it doesn't go like this. So but we need 100 of these 496 by 496 matrices. So probably I should say that this is 100 times. So you need 100 of these matrices on a mini batch of 100 examples. So yeah, it is computationally intensive for an entire mini batch. Okay, so far we discussed about neural networks framed as graphs, as computational graphs, and we discussed about the backpropagation, which is the recursive application of the chain rule along the computational graph in order to compute the gradients for the entire network. We also have implementations that maintain this graph structure, and in these implementations we need to define the forward and the backward functions. So in the forward pass we compute the result for each node in the graph sequentially in order to until we obtain the actual output, and then we do also the backward pass, which is applying the chain rule to compute the gradient of the loss with respect to the inputs. So yeah, in order to apply backpropagation, so actually we first do the backward pass to compute the gradients, and then we update the weights with the gradients, which is actually also doing the update. So there is the forward pass, the backward pass, and the actual update. Okay, and now in the remaining part of the lecture, we're going to discuss more the relation to or actually not this time. We're going to discuss about the relation with biology next time. Now we're going to formalize these graphs as more complex functions. So if we have a simple linear classifier, we saw this notation, function f is equal to w times x. And now with a two-layer neural network, we have this notation. So we have two set of weight matrices. So we have the matrix for the second layer and the weight matrix for the first layer. And we also have here a transfer, an activation function. So this can be graphically represented like this. So we have the input x, which is multiplied with the weights w, and then we obtain the output h. So this is kind of representing the graph with matrix notations. So we obtain this intermediate representation h, which is further multiplied with w2 in order to obtain the classification scores. And with more layers, we can obtain even more complex neural networks. So actually, by adding layers into the network, we obtain this composition of functions. Here we're using this activation for the neuron, which is max of x and input. But actually each layer can have a different activation function. It doesn't have to be the same function throughout all the layers. Okay, so with these more complicated functions, we can obtain nonlinear decision boundaries. And just to prove this, there is this implementation of this two-layer neural network, which models the XOR problem. So here you can see actually this doesn't influence the XOR, the first two value, which are the combinations of x and a and b for XOR. So here we have 0, 0, 0, 1, 1, 0, and 1, 1. And the third component is always 1. So all these points reside in a plane. And the labels correspond to the XOR function. So this is the input and this is the target. So this is our data set. We initialize this two-layer neural network with the weights, with the weight matrices W0 and W1. So these are randomly generated between -1 and 1. And then we apply here the gradient descent, which means that we have to first compute the output of the network, so the output of the second layer. So here this function from the previous layer is applied sequentially. So first we obtain the output for the first layer of the network, which is applying the sigmoid gate on the result of multiplying x with W0. The second layer, so here we're using a trick just in order to eliminate the bias terms. We are adding these components to x, so the bias term is included in W0. So W0 needs bias in order to learn to separate these data points. Okay, so actually this is the explanation why we added 1 here in order to have the bias for W0. So anyway, so this is the output of the first layer, and then the second layer is computed once again using the exponential, the sigmoid gate on top of the output of the first layer multiplied with the weights corresponding to the second layer of the neural network. Okay, so here we do the backward pass. So we have the loss here for the sigmoid gate, which is the output of the sigmoid gate times 1 minus the sigmoid gate. and this is multiplied with the loss, our loss, which is the difference between the output and the actual target. So here we use a squared loss, so when we do this we just eliminate the 2 in front, so we use this value of the loss, and the gradient of the loss with respect to the output, sorry. And then we also have, so this is the local gradient, this is the gradient of the loss with respect to the output, and then we compute the gradient. So recall that these are vectors, and these are also vectors, and this is are also vectors, and here it can result a matrix. So we multiply this matrix with W1 and with the local gradient here. So this is because here we have distribution of the gradient and the local gradient of the sigmoid function. And so here we have the forward pass, backward pass, at the end we have the gradient descent, which is updating the weights according to the gradients. So now we have to distribute the gradients to the input, and this is why we multiply the gradients with the input L1 here for the second weight vector, weight matrix, sorry, and actually W1 is a vector, yeah, I said correctly, and for W0 we do the same approach. Yeah, so here we need these matrix operations in order to be able to train the model in 11 lines of code. So we do not write for every component in the matrix, we use matrix notation. Okay, so the network that is in the previous slide is designed here. So we use x1 as the bias term of this matrix. So usually we define the bias terms like this, but here we replace the bias terms with this third component, and for this unit we remove the bias term altogether. So this is how a normal network would look like, but here we do not use the bias term, we do not need it, and here we model it like this just to simplify the notations and be able to do everything in 11 lines of code. Okay, so commonly here this is a feed, also known as a feed-forward neural network. So the input x here is distributed to all the neurons in this hidden layer. So the input goes to all these 4 neurons, and every neuron receives as input the entire input vector. So this generates a weight matrix of 3 rows and 4 columns. So the number of rows is equal to the number of input units, and the number of units is equal to the number of columns. Okay, so here then we have the transfer function, which is the sigmoid that looks kind of like this, and then in this layer we have a single neuron that predicts the output 0 or 1. So here we have 4 inputs, and all these inputs are distributed to this unit. These are summed and multiplied with the weights, and then we have one more sigmoid gate before getting the final output. Okay, so actually this was the last slide, but I still want to show you not this one, but this other one with neural networks. So yeah, here we have this this input data that we described before, x and y, which is equivalent to the XOR problem. So what I mean here is that these points are non-linearly separable, and we will see that as we train our network, it will reproduce the corresponding targets, so it will approximate them as close as possible. So which means that the network learns a nonlinear decision boundary. So this is the exact implementation that I had before. I just added this for each epoch in the training. I just added these prints in order to see the labels and the actual predictions. So in the first iteration, these are almost random, so close to 0.5. And as we optimize, we see that the model starts to learn these to make these probabilities close to 1, these two in the middle, and the one corresponding to the label 0 tries to make them close to 0. So as we iterate through the model, so after 5,000 iteration, it approximates these 0 and 1 quite well. So in the end, we can just apply, I don't know, a threshold of 0.5 in order to obtain the actual targets of 0, 1, 1, and 0. Okay, so it is possible to learn the XOR with this neural network, which means that the model is able to learn nonlinear decision boundaries. Okay, so this is achieved by putting together more simple neural units that learn linear decision boundaries, but by joining them together into this architecture, you are able to train more complex models. Okay, so this concludes our lecture. Let me know if you have further questions we can discuss. Okay, so yeah, I know we started a bit later, but we are okay now on the time. So we can still spend a few more minutes on answering questions. So let me know if you have any questions. I will try to answer them. So we can also try to ask questions perhaps about the competition. Just let me know. Perhaps this is too early to discuss. You can maybe take a look, and we can also discuss more about it next time. Okay, so I'm going to wait for a few more minutes in case there is a question. Otherwise, we can what is a good result? I don't know. I'm not sure what is a good result. So this is a the good result is I don't know, going with mean absolute error of 0 perhaps. That's ideal, but yeah, I'm not sure how low it can get. So this is the mean absolute error in degrees. Yeah, so I think 1 degree is about maybe 111 kilometers on the map. So yeah, if you have like let's say the top score here is about 0.5, let's say, so this means that the error is about maybe 50 or actually more, maybe 70 kilometers. So yeah, on the map of Germany, I think this is okay. But I think you can probably obtain better than this. I'm not actually sure how low it can get. Yeah, so I cannot say what is the best possible result. So once you achieve it, you may stop there. I cannot tell you that. Um, so are the coordinates always in Germany, or are there people who are in a holiday in another country, for example? I think they're all from Germany. I didn't actually check, I didn't try to overlap them with the map of Germany, but yeah, they're supposed to be from the map of Germany. I'm also not sure how well Twitter is reporting the location, so perhaps, I don't know, maybe if the location is not exact, maybe it will also be a little outside Germany, I'm not sure, or outside the border. It also depends if there is an approximation error from Twitter. I'm not sure if it gets, for example, the location from the IP address, it might have some approximate location. But I think they should be, in general, they should be inside Germany, but I'm not sure if this is really so important. Yes, there will be a second project. As I mentioned in the first lecture, you have to do an unsupervised model as well. But for that project, there will not be a competition. You just have to decide on some data set and on some unsupervised methods that you want to apply. You have to communicate with the lab assistants so that they can agree. So everybody has to choose a different data set, and in order to apply some machine learning, unsupervised machine learning models on top of that. So you have to communicate the data set prior to doing anything about your project to the lab assistants, and they have to we will have a document where everybody will have a chosen data set, and we need to make sure that there will not be overlap. So for the supervised, everybody is working on the same data set and trying to achieve best results, while for unsupervised, each one of you will use a different data set. Yeah, so I'm getting this question for somebody else. These are regular weekly. So will there be? Yes. So you have to prepare the projects, and you will have to present them. So this will be probably during the final the period with the final exams. Perhaps for the first project we will see if we do it before this period or not, but you will definitely have to do presentations. So everybody will be, all the lab assistants will be involved in looking at your projects. So probably we will allocate 10 minutes or 15 minutes for project presentation, for each project presentation. So in total you will have like maybe half an hour to present your projects. But probably we will use different days and in order to see the presentations. Okay, I think I answered all the questions so far, so if there are still any other questions, let me know. Okay, so yeah, same, only on Thursday at the same time. Yeah, so always start at Tuesday at 18 hours East time. How should the PDF look like? Yeah, it should look like very nice. So it should have a few pages with a description of your method, with tables, with figures. Yeah. So you can also check with ideas of what it can contain. You can check the rules and look here. Yeah, so you really need to put some effort in describing your method. Okay, so don't try to be cheap about it and to yeah. Yes, so the code is also required. Yeah, so you need to as I said in the documentation, yeah, so that's me. As I said in the documentation, sorry, so it's this part here. You also need to include your code, so we will also verify your code, so you make sure that there is no overlap with other participants and also no overlap with code from the web. So please read these rules carefully and make sure that you respect them. So this is also valid for the second project, but here you really have to accept these rules in order to participate. So this is the rules that we impose. So yeah, I really want you to implement things by yourself, and I don't want you to implement, to take some code from the web and so on. Yeah, okay, so okay, any other questions? Otherwise, so yeah, I actually took a few questions here, so most of them are about the project. Yeah, so I want to really to see you to participate and see how it goes for you. So I see some of you already submitted some entries with good results, so it means that it is not hard to train models and to make these predictions, but I'm sure that you can actually obtain better results than these first trials that are here. So I'm actually looking forward to see how well you can predict these results. Yeah, so how granular? So yeah, if you use perhaps more than 3 or 4 lines of code, that is already starts to be a problem. So depending on also, for example, if you copy, I don't know, an entire neural architecture without any modification, and you simply copy paste it in your code, so it has tens of lines of code that are just copy pasted from the web, that's not acceptable. So that will definitely imply an elimination. Otherwise, I don't know, if you just use 1 or 2 lines from some resource, that's okay. But I think anything more than 4 or 5 lines starts to look suspicious. Yeah, so I think, yeah, we can, when we do the presentations, perhaps we can organize I don't know, a Zoom session, or I don't know, Google Meet, where everybody can present in turns, so the others can participate and can also see what other people used and what were their implementations. So we'll try to allow participation like this. So yeah, we will not make a summary about it, but you can participate and see what others used. Yeah, there is a minimum page which is actually mentioned here. So I think the minimum page count is Oh, it seems that I didn't mention that. Yeah, so now of course this is also proportional to your contribution. So if you only implement one method and make only one submission, you probably don't have much to talk about. So I think maybe a minimum page count will be 2 pages, but I don't know, I've also seen reports of more than 10 pages in previous years. So it really depends on how much you work on the project and how. Yeah, so but I don't see it right now. Maybe it was mentioned in the slides somewhere in the first slides. Yeah, so it's mentioned here. I didn't read this. So yeah, a minimum of 2 pages, excluding tables and figures, is expected. Okay, so I knew I read it. So I wrote it down somewhere. I just didn't saw it right now. Okay. Okay, any further questions? Maybe about the lecture today? You're only asking about the competition. Yes, of course. So in the end, you will. Yeah. So the documentation actually is also to show that. So yeah, I presented some way of working with machine learning. So you have to do hyperparameter tuning. You have to try different models. You have to I don't know, use different features, and really the documentation helps us to understand more about how you approached the task. So the main idea is to document what you did. Even if it's something failed, you still need to include it and show, look, I also tried, I don't know, random forest with bag of words, and it provided, I don't know, bad results. And these are the results on the validation set, and they are not so good. But then I tried, I don't know, to add something else, and it improves the results. And then I also replaced random forest with SVM and so on. So this kind of everything that you test should be included in the documentation. And even if you don't make a submission, you can still report the results on the validation set. Yes, of course, you can also add references. So you should also briefly describe the approach. So what is the model that you include, how you extract features, and so on. And also a brief description, like maybe 3 or 4 sentences about the model, so that you show that you understand how the model works, and you didn't just apply it using, I don't know, from scikit-learn, fit and predict without knowing what the actual model does. So if you apply a model from the lectures, of course, you are sure that you understand it. But if you also apply different models, we also want to make sure that you understand what that model does. So you have to be able to explain it. So you can explain it in the documentation, but if you do not explain it properly there, we can also ask you during your presentation. Of course, yeah. So Okay, so oh, sorry, yeah, I thought it was a question. This one, yeah, so it was just a comment about the mini page. I saw it now. Okay. Good, so yeah, just wait one more minute. I hope I didn't miss any other question. It seems not. And we also don't have any other questions, so I think, yeah, so far I think you have enough details at least to start working on the competition. What can I say? Good luck in the challenge, and see you next week with more information about neural networks. So we still have 2 more lectures on neural networks. So this is a bigger subject that is treated in 3 different lectures, and then we will start discussing about unsupervised approaches. So I think, yeah, in week 10 you can also start choosing your data sets for the unsupervised projects. And the deadline for the deadline for this project, so you have to perhaps I didn't make it obvious. So here you have the end date of the competition, and 2 days after you also need to have your documentation submitted. So on 5th of January the documentation should be ready, and we can also set up the deadline now for the second project. So for the second project you have to choose the data set by the end of the year. So this is 31st of December, and you can submit the documentation by let's say so I think the semester will restart on 4th of January, so there will be 2 weeks. So you should have your documentation ready on 15th of January for the second project, and you have to choose your dataset, as I said before, until 31st. Okay, so yeah, you can work for both projects in parallel. Actually, I think it might be more useful to do that. And yeah, we will schedule the presentation probably starting from Saturday in some we will set up some date for the exam. So probably actually we will need 2 dates for each project, or otherwise we can also set it in the same day, but I think it will be more stressful for you, so perhaps it is better to do it in 2 different days. Okay, so thank you guys for participating, and see you next week.